Hi, this is the magnetic cannon, and in this experiment, balls are rolled down this track to this magnet, and then on the other side, we'll see this ball accelerate this way down the track. Let's see it happen.
Hello guys, at the Exploratorium we saw a experiment called the magnetic cannon, and today I'm going to be explaining how that worked. So the experiment started set up like this. There was a ball on one side of a track spaced far away from a dividing magnet with two balls on the other side. When the experiment started, this ball rolled down the track colliding with the magnet, and then we saw this ball go off this way. And you'll notice in the experiment, the speed that that ball was going was a lot faster than when we rolled the first one down the track. So starting over, when we roll the ball down the track, you might think, oh, well, that's a problem. That's just a simple collision problem. But then you realize that the fact that this one goes faster seems to, you know, like defy the laws that we often hold for collisions, which is that, you have to conserve kinetic energy, you have to conserve momentum. However, what you're not thinking about is the role that the magnet in the middle plays. Um, so as the ball comes closer to this magnet, it actually, the balls are steel. They actually get accelerated by the magnet. So, it's rolling down here at this speed, and then as it gets closer, it suddenly speeds up. So the magnet is actually doing work on that ball, which means that even if you only put in a little bit of, you know, you only put a little velocity this way, by the time it gets to the end and reaches the space by the magnet, it's going a lot faster than you roll it with. And then it really is just a matter of collision. You have a ball, it's going really fast, it collides, and similar to the experiment called Newton's Cradle, where you have the ball suspended on the strings, the energy actually passes all the way through the magnet, um, through the magnet into the other ball, but then, you know, the other ball, collides again, and then finally you interact with this ball and it speeds off down the track. So really, this experiment is just a singular collision or singular ball that is accelerated by a magnet, and then a series of collisions all the way through until you get to this one. And that's why this one has so much speed. That's how the magnetic cannon works.
Hi again. I'm here at the pendulums with varying weights, and in this experiment, we're going to be looking at how changing the mass in the end of the pendulum does not change its period. So to start, set both pendulums to one side and release them at the same time. And we can see that they have the same period. Now, start over, but we add a mass to one of the pendulums, we're going to see that even now, they still have the same period.
Okay, so our second experiment we chose were the pendulums of varying weights. In this experiment, we had two pendulums, um, both of which were set up in this like figure eight configuration where there were two slots to hold added weights. Um, and what I showed in the video was that even if you put weight in one of the pendulums, they would have the exact same period. Um, and this is important because it draws on um, one of the laws of simple harmonic motion, where um, frequency and period are independent of amplitude. And this all makes sense from the pendulum standpoint, because even when you add the weight, you're increasing the restoring force, but you're also changing the momentum and moment of inertia, which mean that, even with more weight, you come out to the same period. And this is reflected in the equation for period in the equation sheet. When the equation is 2 pi square root of the mass of the pendulum divided by, or sorry, the square root of the length of the pendulum divided by gravity. And this makes sense when you look at the results. Um, the lengths are the same, and mass has no impact on the actual period. Now, something interesting that I didn't show is that if you were to move that weight up one, um, then the period actually does change. And this is because that length is calculated based on the center of gravity. So as you move that mass up, the center of gravity actually changes. Whereas keeping the mass at the bottom, the center of gravity in the same spot. But as you move that mass up to the higher hole, the period changes because the length, which is to the center of mass, has gotten shorter, resulting in a shorter period.
What's up, guys? Today we're looking at the gravity-powered calculator. Now, this is a machine that uses kinematics and conserved energy to, based on where the ball is placed, determine where it will land. So, to demonstrate this, let's start here. So, we've chosen the number 36, and based on where the ball lands, it's going to tell us the square root of that number. So, we all know the square root of 36 is 6. And now we're going to release the ball, and you're going to see it land on 6. Let's do that again. We're going to start at number 4. Ends on 2. And then one more time, let's do number 16. Should land on number 4.
All right, for our final experiment, we had the gravity-powered calculator. That was one of my favorite experiments there. I thought it was really cool. How they actually use really basic physics principles, such as, conservation of energy and kinematics, to quote unquote do math with this ball on a ramp. So in the experiment, this ball rolls down this ramp, and then the very end of the ramp, I don't know if you can see it in the video, it's actually flat. So it goes off the end of the ramp and then, falls wherever it's going to go. And now this makes for a really great experiment for a lot of reasons. The start is that, the principles that use are really basic. The first of which being conservation of energy. So as the ball rolls down the ramp, it's just a super simple like conservation of energy problem. It starts at a height and you just do mgh equals 1/2 mv squared, and eventually, at the end, you have because it flattens out, it translates all of your, energy, all that velocity. You don't have to worry about the angle because it's all translated into horizontal kinetic energy. And that's really great for the second half of this, which is the kinematics. Now, the second part is that, this ball is going to fall a certain distance before it hits this long setup with all those bars that you saw in the video. Now those bars are set up at specific places so that when the ball comes off that ramp with purely horizontal distance, you know that the only downwards acceleration acting on that ball is gravity, and that allows you to set up uh, you know two equations, two kinematics equations using delta x equals v naught t plus 1/2 at squared. You're just gonna, you're gonna do two of those. The first of which, you're gonna have no acceleration because it's the components. The delta x is gonna be here. That's your first delta x. And then, there's no v naught again because all of that velocity from rolling down the ramp is horizontal. So you're only going to have acceleration due to gravity. So then in your equation, you set your delta x to the height it travels, and then you set your v naught is 0, and then it's just delta x equals 1 half at squared. You solve for that, you can solve for t, and because it always follows the same delta x, that time will always be the same. Then, you know, after that, you're just solving, you're taking your time and you're using your v naught, which you calculated with your energy equation, um, to solve that, as the ball rolls down the ramp, it comes off, the time it goes will always be the same. So whether it goes there, there, or there, it's always spending the same time in the air. The question is only how much horizontal distance does it cover? Um, and the way this corresponds to the height on the ramp, you know, the higher that it is on the ramp, the greater your v squared is, which means the greater your velocity is, which means the greater distance it travels. Now, the reason it's a square root, um, I'm pretty sure they could have picked whatever. The square root is nice because it's one number that becomes another number. You don't have to pick two numbers, you just pick one. Um, but also, this thing here, the ball, its root 2gh is going to be your velocity. So it sort of already travels in square roots. It makes it really nice to solve. But yeah, as this ball travels down the ramp, it comes off. You solve for your time using your delta x, and that's how you know where it's going to land every single time. At the top, it's energy. At the bottom, it's kinematics. And that's how you solve um, the, gravity powered calculator. Thank you.